So now this is the important topic from governor that we need to consider. That is the stability analysis of a governance. Stability analysis is that stability equilibrium. So there is the equilibrium, and that is that the system returns to the initial equilibrium position by the own whenever they disturb from their original position. That is the same, and it is the stable equilibrium. So now it is the equilibrium position, that is the stable equilibrium. So where it will just move here, it will just really come back. But here, what is that is unstable equilibrium. Why? Because you have to move this body here, then you have to put some effort, then to get it back to here. So that's why it is an unstable condition. So it is written here, that is that. If it is that we need to do some work on the system to bring it back. That is the point. Then there is the neutral equilibrium. Is that it is the here it is in equilibrium. Then it will here that will be also in equilibrium, but to bring in the system back in equilibrium, we need to apply some work also on the system. That is it. Work required to bring the system back into initial equilibrium is more than unstable. So work required to bring the system back in initial equilibrium is more in unstable equilibrium than stable equilibrium. So what is in stable equilibrium? It will need less force to just get back into equilibrium. Stability analysis, now it is get back to this point. So here what is the FC, that is centrifugal force, F R, that is totally radius, FC and F that we are just seeing. So what will happen? There is a 3 point that you have to consider. So RE equilibrium that you can see here, that is the RE equilibrium. So what is happening? That this point and this point are just coinciding. So here in this point, there is a coinciding. FC equal to F, that is the equilibrium. But at this point, that you can see that FC, what you can see now? FC is more. What is more? FR is more. FR is more than FC1. That is the same. FC equal to MR also. So it is great. So controlling the force will be, so controlling force will be dominant and the force reduce the radius of rotation. So radius of rotation, this is the curve. So controlling force, that is the FR is more. So FR is more and dominant. So that will try to reduce the current. So FC is zero. So what is happening now? So even if I just show you in a picture, so that is the thing. That is the FC force. That is the FC force. That is the FR force. Yeah. So what will happen if FR is more? FR is more here in this case. So what will happen in this case? The FR graph you consider as a curve line. That is the FR graph. So if FR graph is greater, then what will happen? It will try to shrink the radius. So that's the exactly thing it is happening here. And in this case, what you will see that in R2, then FR is less, the radius is less, then is the centrifugal force, that is the more. So what will case? It will just try to increase the radius. It will try to increase the radius. That is the main point that you need to consider here. Okay, now let's get back. So let me just put it here. So now what will happen? This is the graph. Then it is the graph that you can see that FC here. That is the angle. It is the angle for FC, and it is the angle for FC, and it is angle for FR. So we are just pointing here. So on this equilibrium position, what will happen in equilibrium position? The angle of theta, angle of theta, it is a theta angle, it is less, and angle phi, this is the angle phi, here it is happening, angle phi, that is the mode. So condition for stable governance, the slope of the r, so the radius is greater than the in equilibrium position than slope of the first line, straight line in equilibrium. That is the point. Df by d of r, df by d of r, that is here slope of the r, so theta, yeah. F of r slope, so f of r slope is greater, f of r slope is greater, so equilibrium, so slope of the r is greater in equilibrium than slope of the straight line, that is fc of by r, that is the straight line, that is the slope greater. So we can say that d by d of a is equal to x m omega square r. So why? Because it's r and m omega square by r. So where m omega square divided by r, so r are cancelling, so this is the equilibrium position. Then here, the group for FR and FC and FR then connect is more than one location. So what is then that FC and FR there you can see it is intersecting is this person also, this person. So this cannot ever can happen for one omega speed. One can omega speed that cannot be happening. So for each omega angular speed, there will be one single intersection point. That is the very much crucial point. And now that is the stable governor case. Here you can see there is a FC, there is a FC2 and there is a FC. So what is FC equal to this side? This is the Yeah. So what is the that omega 2 is greater than omega 1, so we are equilibrium 2, so r equilibrium 2, what is happening, it is the r equilibrium 2, this is the r equilibrium, so in each cases the equilibriums are greater, so for omega 2 the equilibrium is more, so it is the fourth stable level, so as equilibrium is increasing, as the equilibrium is r equilibrium is increasing, omega 4 also increasing, with omega 4 increasing the r is also increasing, and it is unstable governor. Why? Because here R2 is less effort and in this unstable governor. So what is happening here? So you can see here that is the graph, it is happening here. So it is theta and it is the theta. So what is happening? It is phi. Effort is less. Effort is less. So what is happening? Theta is less than. So cannot be unstable governor. So mathematically conducting for unstable condition curve. So of the effort. So of the effort curve you can see is less than the slope of the straight line curve. So that's why it is the unstable governor. Now one more unstable governor here you can see. So equilibrium. So governor equilibrium equation that for a particular radius it is say a per a for omega square, and this is spring control governor, it is the spring control governor because toward in the straight line. A for is a plus b, this is also straight line, f is equal to a1 plus b, so it is also straight. So a for that is the phi, and for so here what is happening, so slope of the a for slope of the a r is less and slope of the straight line is low, so tan inverse, so here you can see tan inverse a equal to tan inverse a in omega square, so it is the unstable governor because a for is less. Now, what is happening? F of AR minus B. So AR minus B. So it is this minus B by A in this point, and this minus B. So here what has kept me? There is a theta is less and phi is more. That is A for is AR minus B is more. There is a stable governor. There is the equation. And for active governor, so here you can use if greater than zero. If is for a active governance. Active governance is what you can see. If it cannot be reduced, cannot be less than zero. It is the if has to be some point and has to be always greater than zero. So if r is greater than zero, whenever it is less than zero, that is not going to be stable governance. Okay, in this neutral position, so for any equilibrium, so f r and a there is coinciding. So equilibrium, one of which always in neutral position is termed as isochronous governance. Only possible when spring enclosed. For normal governance, it cannot be possible. For mass and ball governor, that is even spring that is not possible. So if equal to a plus b unstable, if equal to a minus b, so you can just add plus b, then get the unstable governor and isomer governor. So here you can see plus b plus b. So what will happen if both are plus, that will be unstable. 1 plus 1 minus, that will be stable. And 1 plus only, that is also isochronous governor. So this is the fourth test. So an unstable governor will become isochronous if we reduce the controlling force. So we have to just reduce the controlling force and then it will be stable condition. So all these things have to be read in this chapter.